it in. So now what I'm going to do, you guys, is I'm going to grab the data, just like we had before. And now my environment, all of a sudden, after this command finishes, is going to have, boom, two objects are available for me here, okay? One is the actual raw data, and I can view that. So for example, I can type, oops. View. So view, look what happens now. And if I start typing, our studio is very smart. If you start typing a few keywords of an object name, it's going to suggest what it might be. So for example, I have capital D, data, and it tells me what I can choose from, right? Does everybody see the list? So of course I want to view the data that I just downloaded. And it's going to show it to me as a spreadsheet in the top left canvas here, right? So let me kill this, it doesn't have anything. So I know that here's my data. If anybody wants to see what was the data behind the graph that we saw a second ago, it's the 20 years, actually 21 years. 95 to 2005 is 21 years. Let's make sure we get the years right. And R, I was in grad school when R came to be as a language. It evolved from something that was called, the statisticians were developing something called the S language for statistics. So R, two guys, their first name started with R, and the hypothesis is that R comes near S, anyways. It became known as an R, and it's the open source version of the former S language. So that's how you can view data in a spreadsheet format. Now, sometimes you just want to make sure that what you intended to read is correct. So you're not going to be copy-pasting here, or this is not Excel spreadsheets. This is just to show you, roughly speaking, the column names, and roughly speaking, the type of data that you have, right? And you can scroll if you want. Anyways, so back to the little code here. The next thing is this melting. Oh yeah, so let's go ahead and do this. So I'm going to run this command line. Again, highlight the command line and press the run key, the run button here to send it from the source file onto the canvas and run it. You can also with the mouse copy paste it. So let me demonstrate this. Control C, click on the canvas, Control V, paste it in, hit enter, and then let's just view this new data frame. Notice how, so here is the original, you guys. It came in the white format. For every year, I have one row of 3 records. When I convert it from this white format to the long format, it looks like this. I have a year, and then I have a name and value pair. The name and value pair is for which language or which environment I'm talking about, and how many citations were there. So now, remember, we went from a matrix that's 4 by 21, which is 84, right? 84 things, into a matrix that is 21 times 3, which is 63 rows, should be. Oops, hold on. 45. Oh, okay, I didn't scroll down all the way. 63, okay. Just to make sure the math is right here. And so it's the same data, it's just slightly morphed, okay? Is everybody here with me? So, all right, so next I'm going to go down to the actual plotting, and now I'm going to just click on the run command, and now look, I'm now in a pack. I'm going to get to some of these guys later. I'm in the packages tab on the bottom right corner. If I run this plotting routine, it's going to switch me from the packages to the plotting, And now here is my graph that we just generated. I typically click on zoom, and zoom you can maximize, and then right click to copy it as an image or save it, or I suppose. Oh my gosh. Okay, so that's different on a PC. Okay, it goes probably in some kind of a download directory. Anyways, look, I can copy it, and if you have let's see. Let me just. I meant to open Word. I just need a place to paste this image just to show you that it's in my mouse buffer, and I can include it in a publication or something like this. Okay, blank document. Oh, create. Okay. Sorry, this is a bit different, the interface. Okay, so I have in my mouse buffer, so I'm going to do Control Paste. So here is the image, right? You guys, you can save it, whatever, PowerPoint it, whatever you want to do. Okay, so let me close Word to release resources again. Don't save, and close Excel. Okay, so this is my zoomed in version of the dynamically generated image. Was everybody able to generate this image? I mean, you know, the syntax is not as important right now of the specifics of how this image is generated. The important thing is that there was data living in the cloud. We downloaded the data. There was some packaging, some data manipulation, data wrangling. We went from wide to long format, and then there was a plotting. That's the important thing now. Okay? And then kind of to get oriented in this syntax here, I typically, if you don't need something, get rid of it. That's, you know. So this file I can save. Yeah. So this should be on my, replace the original one. So let me see if I can see where is this file now. Oh, I see. You open a new thing for me, right? I beg your pardon. I didn't see. Okay. So I'm going to drag it in. Okay. Is that how it works?
Yes, that's good.
Okay. All right. So I'm going to be saving. I have a folder here. Okay. All right. So let's see. So we've got the layout. Okay, some notes about syntaxing. The assignment operator in R is less than followed by the minus sign. So this is a right to left assignment operator. You can use equals as well, but equals sometimes has a different meaning, that plug in that value that's on the right side into the name that's on the left. So try to get used to this operator, although sometimes you see we use them interchangeably. So here's, for example, the assignment of X is going to have the value of 2. When you need help, you can either type help on a topic or just use the question mark. So here is my RStudio. I can do okay, all right, so let's go ahead and close it, but I'm going to open it appropriately now. Open it from the desktop over here. So it completely from where in RStudio kind of monitors these files. It says you don't know what you're doing. It's right. Okay, so yeah, I was going to do a help. So you can do help. And you see how it always, look at these pop-outs. These are very helpful things when you don't know the exact syntax of a method or something. RStudio provides these very helpful. So for example, if you know which package is the topic in, you can provide it here. In general, let's say I'm looking for linear. Suppose I just type linear. Okay. The string completion Okay, so why don't it says I don't have anything on linear in this exact phrase. So I'm going to do a question mark, linear, and you'll see that I'm going to get exactly the same outcome. It's going to say nothing known, but if I put a double question mark, it says, so I'm copy pasting all the time. You guys have to get used to copy pasting just to get quicker responses. Now here in the help, it's going to tell me everything that has to do with linear. So look, I was actually going after the stats package linear model, but I didn't want to type LM for linear model because that's presuming I know how to call a linear model. I didn't. So right here, you see, it kind of tells you, so I can type in the search query here, linear model. Linear model, and then it narrows the search, right? There is much fewer things, and the thing that I'm looking for is this specific thing. And by the way, look at the forward and backwards arrows. You can always go back to where you were in the help, in the plots, in everything that you've done. You can kind of go back. It's almost like a browser with its history for going back and forth. These are very useful things to remember. So I just wanted to get some help on the linear model. This is the simple function that I wanted to get help on. So it tells you it's part of the stats package, which by the way is always loaded by default, because after all, R is a statistical computing package. So the stats package that comes with all the basic statistics comes preloaded. And it tells you a little bit about the package and how to use it. For example, you put in a formula, you provide a data set, and various other optional arguments. All of the arguments are defined, and then what this method returns to you is called the result of the call, which follows after the details. It says the value returns an object of certain class, and it ends with an example. So this example everybody should be able to run. So here's an example where we have two groups, and by the way, you guys, if you bring the mouse over the center, you can maximize any one of these panels. You have to be careful with this because it's going to shift your code in the top left panel a little bit, so you got to be careful navigating, but sometimes if you want to read more of that, you can kind of zoom in a little bit on the window. So what's happening here is this has two column vectors. C means a column vector with these how many values? I don't know how many values, but let me go ahead and run this. I can copy it with my mouse and put it in my console over here. Hit enter, and then under the plots, these are some of the plots that were generated from these data. Now, mind you, it computed over here a generalized linear model for these data. So, and now I said, well, how many values are here? This control and the treatment, I can actually do print the length, just type length. And you see, as soon as you type 3 letters, it suggests for you the most appropriate things that you may be working on. If you press tab, if it has highlighted the right command, I can press tab to complete it, and then inside I can just the name of this variable was what? It was called CTL for control. 10 observations, okay? I'm sure the treatment, the second variable, also was of size 10. Oh, and by the way, the up and down keys on your keyboard run the previous commands. Okay, so you see how I type this? I just pressed, and if I go farther back in time, see, it tells me what I typed in the past. Just the up and down keys, you guys, so that you save on typing. Okay, so I want the length of the treatment. Should be 10 as well. Okay, so again, here is the canvas with our source code. We can run some of this. Here is the canvas with the environment or the history of what we've ran. And here is the help packages and plots that we've generated. Oh, look, you're going to see this many a times, and it is difficult, okay? Look what happens. I reduce the margin of my plotting window, and it says figure margin too large. The figure was too large to be plotted in this small canvas. So if you see this, there is two solutions. The first silly solution kind of is to zoom in that, and then the figure is going to render. Okay, but the better solution is to redirect the plotting to an external file where you control the resolution, the size of the image, and everything else. We'll talk about that. I just want you to know that you have too much stuff packed into your desk environment, and sometimes you will get that problem that I just showed here. Okay. So, and I'm not sure if Zoom is going to work. Okay, Zoom works. Okay, that's fine. All right, so any questions about the organization of the RStudio graphical user interface? Yeah?
I can't seem to get the GG1.
Okay, let's have a look. Did you download the package? Okay, so
It's what it says here. I can get the
okay, can you click on packages? I want to show you. Find ggplot. Yeah, click it off. What's it say? Can you try to run this require ggplot? Just highlight the first line. Highlight the first line and click run. So I don't know what happened. Now it's started off, so it's working now. Strange. I'm not sure why. Because you see, the library and the require should work the same way, but in your case,
what I did was I did show us like the other one, I love this.
yeah.
I did that. But the last command.
The actual plot. Oh, can you run it now? Yeah. Oh, yeah. Okay, so that's an important point. He reminds me that sometimes, you guys, if you run a plotting here and you click run, it will not render it in the plotting window. If you want it rendered in the plotting window, you have to copy and paste it here, because this is the window that puts stuff here. This is just a source code. So let me just demonstrate this. If I click run, you see nothing gets plotted here, because it actually gets rendered see invalid graphic state. If the file that I'm editing now was an R markdown, RMD file, it would have plotted it right up here in the source code itself. We're going to show you examples of this. So to get this to plot, I need to do Control-C here, paste it in here, and hit enter, and then Oh my gosh. Oh, okay. I have to reset the graphics. Hold on one second. Hold on one second. All right, so I had, remember how I ran one example that generated the linear model plots? It changed the layout, so I had to refresh my plots canvas by clearing everything. And you see these arrows are not disabled because I don't have a previous plot and a following plot. So that's why, again, that's a good point. So does it make sense why running it here does not generate the plot in the... I'm going to go back to the notes. So here's another example. Let's just look at this. This is, you know, kind of simple terms. Another example showing this melting of data set from long to wide. But this time, you're literally generating a data set on the fly. So you see, remember before we used the command called read CSV to read the data from a local file or a cloud service. In this case, we're going to be using read table, and the table is actually given as a text file that starts over here and ends right after the quote. So it does have a header, and by the way, these booleans, there is many arguments of functions that are Boolean in nature. They're either true or false. The capital true and capital false are reserved commands in R. You can abbreviate them to capital T and capital F if you want. So we're essentially generating a text. This is free text between the quotes. This is the start, and that's the end of the free text. The actual text is in between what I'm highlighting here. 5 subjects, 5 rows, and then 5 and 5 columns. Case ID, the first one, gender, age, condition 1 and condition 2. And then what you want to do is, you see this function factor, it essentially indicates that the case ID is going to be considered a factor variable. And mind you, this is very R-specific notation. When you have an object called raw data underscore wide to indicate that the data is in the wide format, 1 row per case, including all the features, all the time points, all the characteristics on the same line, then so you have this object called raw data wide. If you put a $sign and then a column name like case ID, it simply refers to the column, the first column. All of its values are going to be considered to be factored. You could have done factor for gender because gender is obviously a factor variable. Well, actually, let's take a step back. Does everybody understand the types of variables? Quantitative, qualitative, factor variables, discrete, continuous, categorical. Is everybody comfortable with that? With these descriptions? Any questions about, so factors typically refer to categorical variables that may or may not be ordinal. They may or may not be comparable in terms of comparison bigger than or equal to. So we are just constructing a new variable called subject. And you see, we are going to add it to the old object called raw data wide. We're going to call subject to be a factor representation of the case ID. And now if you go ahead and print, just print the name of the raw data variable, it's gonna print out the very same 5 columns that we had before, plus the extra column that we just generated, which in this case equals the case ID, but it could have been something different. Now, again, the reshape2 package has the melt function, and that's a very interesting function. It allows you a lot of flexibility when you want to reformat or restructure data. In this case, we are simply going to be using the case ID and the gender as variables that are not long expand. So these are going to be the ID variables, and everything else, which includes okay, case ID and gender we're going to preserve. So case ID and gender. The other variables, age, condition 1, condition 2, and subject, they're going to be expanded from the wide format down in the long format. So you see, again, subject 1 is a male, and then they are going to have how many new rows are we going to have for subject 1? Well, we're going to have a row for each of these variables that we did not ID on. So 4 rows are going to have the labels case ID is 1 and gender is male. So here is the first one, namely storing the variable age. Here is the second one, storing the condition 1 for subject 1. Here is the third one, storing the condition 2 for subject 1. And the last one is right up here, storing the subject ID. So again, this is a reorganization of the data. And here is a little bit more of a description if anybody wants to go deeper into the melting package. So the ID variables are the variables to keep but not split apart on. In our case, gender and case ID. All the other variables, including age, condition 1 and condition 2, are going to be split on. And then you can simply print this long variable that you call. And now look at the assignment again. The label data underscore long is going to be the name of the new expanded data format variable, and you print it, and it kind of looks like this. So you don't change the data values, you don't change the amount of data, you change the configuration of the data. Now there is a package called well, the article is called tidy data, but the package is called, there are several packages that do tidying of data. So you may want to read this article if you're interested in getting a little bit more about data manipulation. So let's go over some of the simple things, like creating a new column vector, which we already saw when we talked about the linear model. C stands for column vectors. Data in R is stored as columns always, and the first index of the column is always 1, not 0 as it is in the C language, for example. So here is where you construct a new column A that has these 10 or so values, and typing the name of a variable always reports its content. So be very careful printing stuff, because sometimes these data objects are very large, and if you print it, first of all, it may take a while to go through the thousands of lines of information that these structures may include, and second of all, if you have too many columns, they're not going to print right. So typically people don't print the values of a data set. And you can use, there is lists, there is repeats, you can recursively label things, standard things, you can construct sequences from 1 to 10, for example, using the seq command. You can specify the step of the sequence. This is useful if you want to construct a variable that gives you the time points at which certain observations are labeled. If you only have the recorded measurements, but you don't have the time points at which they are recorded, you can use sequence or repeat or something to generate time points, and then you plot time versus observation using the plot command. We're gonna have some of these examples. The length function we already saw. It tells you how long is a univariate single column vector. If you have a matrix that's two-dimensional, you need to use the dim for dimensions to print its size, right? So linear objects have length. Planar objects have areas, right? Which corresponds to the dim for the dimensions. Objects that are three-dimensional are also going to have dimensions, right? X size, Y size, and Z size. So these are common things that commonly are used throughout. You can construct sequences, repeat various measures. In fMRI, for example, you typically repeat the same time points, but the specific paradigm that's applied at each time point may have to vary. So data frames. So what are data frames? These are objects that are created either from matrices or from other, they're called tensors. A higher order matrix is a tensor. Think about a three-dimensional lattice where your indexing for the intensity is indexed by the x location, y location, and z location. This is a tensor, and you can make a data frame out of it. The data frame is a little bit more than just the values that are included as intensities. For example, a data frame can contain row names, plane indices, and cross-sectional. You know, if you go from sagittal to coronal to axial, it may have some additional metadata. So a data frame is the actual data plus some metadata describing the data. That's the way to think about data frames. So here's an example where we create a silly data frame that has some numerical values in the first column. In the second column, you simply have 4 characters. There are 4 strings actually, but each string is a single character string. And the last column is just the values 10 and 11. Now, when you do this, a data frame is always rectangular. Look, the first column, it has length of 4, right? Because I have 1 to 4 in increments of 1. It goes 1, 2, 3, 4. So the first column has 4 elements. The second column also has 4 elements, but they're categorical. And the third column has only 2 elements. When you have 2 elements like this, they need to be, R allows you to do that, but they need to be, the number of the other rows need to be divisible by that number so that you can stack them together. So for instance, let me show you how this command is going to fail if I put a third value in the last column. So right up here, if I try this, this is going to work nice, but if I add up an extra number here, so it's going to complain because I have 4, 4, 4, 4, 4, 4, but the last one has only 3 elements, and there is a gap here in the corner. Is everybody here with me? That's why it's going to complain. If I only put 1 element, it's going to replicate it. It is going to replicate it 4 times. So right up here, if I put in 12, it's going to replicate, oops. And now that's interesting. So what happened now is I have opened a bracket, something happens, but the bracket is never closed. When I press enter, R understands I haven't finished my command line, and it says you gotta keep adding. And the thing to add right now is a closing brace, and that's gonna be okay. The number 12 is gonna be repeated 12 times because 4 is divisible by 1, the size of this object. Right? I mean, this is not very interesting, but to kind of give you a little bit about the syntax that R uses. Let's keep on. This is important now. Arrays, because all the neuroimaging data is given in arrays, right? And they're complete arrays. You don't have arrays where there is a missing value here. The machine will generate complete data. It may be wrong, but it will be a value here. So, so you have the row indices, okay? You see the first index, 1, 2, 3, 4, 5, kind of shows you the row that you're in. And then the column indices are the second index, 2, 3, 4. And then the plane, you know, the section, kind of gives you the page or the depth or the plane index. So that's the last index, second plane, third plane, etc. If you have a four-dimensional object like an fMRI time series, you're going to have an extra element here that's going to be indexing the time point. So you imagine this three-dimensional matrix and one time dimension, time 0, time 1, time 2, etc., right? So it is very important that to understand that these indices are not swappable. If you swap two indices, you're jumping around in this matrix, right? So look at the element 1, 1, 2 and the element 1, 2, 1. They're at completely different locations, right? So in the C programming language, the first index is always the fastest varying index, and the last index is always the slowest varying index. When you store matrix data in memory, it's always stored linearly. So think about unfolding this stack of planes, each plane representing rows. The way you unwind it is you write the first row, and then the second row gets pasted right up here. The third row is after that. The fourth row is after that, etc. And once you exhaust the first plane, you go to the second plane, get its first row, paste it in here. Second row goes after that, and you string them all together. You're going to have exactly as many indices, exactly as many entries as the product of the dimensions. In this case, 1, 2, 3, 4 times 1, 2, 3, 4, 5. 3 times 4 is, no, 4 times 5 is 20, times 3, 60 elements. So if you unstring that matrix, it becomes a 1 by 60 array. Does everybody get that? And how you recut that 60, this array of 60 elements, if you cut it into fragments of 4 versus fragments of 5, you know, you're going to get a different rendering of the same volume. So you got to be careful a little bit with these things. But this is the typical indexing. If you, in R, if you skip an array, you're referring to the entire column here. So for example, the object that's referenced by 2 blank 1 is going to have the second row, the first plane, you guys, the first plane, because these other planes are plane 2 and plane 3, right? So I'm looking at the first plane, second row, any column. So I'm referring to these 4 observations, these 4 intensities. Is everybody here with me? Now, if I had left blank here in the beginning, this would simply refer to the entire first plane, any row, any column. Right? Okay, so this is a very shorthand notation in R to traverse and aggregate multiple things. Now, they need to be cardinal projections. You can't say this and this and this. You got to explicitly list the indices, but this is a shorthand notation for the things that are kind of vertical. All right, so here are some examples and whatnot. Reading data, we've already seen the reading data command. Oh, this is important. Here we've actually printed some statistics. If you do summary of any object, the object could be the result of a linear model, the object could be an array. Summary of anything kind of gives you a succinct representation of what's in it. So in this specific case, we've loaded a data set from the cloud. Let me copy paste it into my RStudio. Okay. Let me copy paste it. Oops. downloading the data. Oh, and by the way, sharp, the sharp over here, the sharp over here indicates everything after a sharp is considered a comment. And that's why in the notes it's gray color or something like this. So if you want to say what it, so okay, back to here now. It downloaded the data and it told me that this specific data set has a whole bunch of variables. Tumor size is one of these variables that it has, and it reports for you some simple statistics: the minimum, the first quartile, the median, mean, third quartile, and maximum. Now, does everybody know what the quartiles are? The first quartile is the value that separates the data into the smallest 25th percentile and the largest 75th percentile. The second quartile is the value that has half the data bigger than it and half the data smaller than it. The second quartile is also known as the median. The third quartile is the 75th percentile, meaning only the largest 25% of the largest observations are to the right of it, and the remaining 75% are smaller than that value. So the quartiles, which you have three, Q1 is the first quartile, the median is the second quartile, and the third quartile is Q3. They tell you something about the distribution of the data. In fact, the difference between the third quartile and the first quartile is a measure of dispersion. It has the central 50th percentile of the data, and if this is wide, it means that the data is highly varied. If the interquartile range is what it's called, is tight, your data is most likely very tight, less noisy. Also, you can do the same thing with the minimum and the maximum. The difference between minimum and the maximum is another measure of dispersion or variability. And if you have missing values, it would report just below the maximum, it would report NAs, NA for not available, NAs, and it's going to tell you how many missing observations are in that feature, in that variable. Remember, you can also use the view command here. And another important command is just head of this what is it called? Data. .csv. If you just do head of an object, if the object is data, it reports by default the first 6 rows of your data. You can also use tail and report the bottom 6 rows of your data. This is sometimes useful if you want to troubleshoot, just to make sure that you got all the subjects or something like this, or the data. You can also use column names if you're only interested in the names of the features. Oops. Data, CSV. What are my column names? These are the features that are available in this data set, right? And you can use, remember the view also, you can load it as a spreadsheet if you want to. Okay, just a few closing remarks here. You know what, for now, let's not worry about too many of the technical details, but I want to tell you that in R there is a very clever syntax that allows you to subset a data or generate cohorts that meet certain criteria. For example, you can say, pull out of my data object all things that are in the following columns. I can say, pull out all the data that has between these two values. You can pull out certain columns. You can pull out the first, the fourth, and the second column only. You can manipulate the data very effectively with single command lines, just to stratify and extract the data that you're interested in. For example, if one of the columns has the gender, the sex of an individual, and you're only interested in the females, you can specify here that you're interested in the gender equals to male or female, and it's only going to pull out these values. Okay, so there's a lot more things that we can look at. I'm going to skip over most of these. There are standard mathematical functions and statistical functions. The binomial coefficient n choose k is very frequently used. In how many ways can n objects be arranged k at a time? There is a choose command. There is the maximum. It finds the maximum of an array, the minimum, the range. The sum is a common characteristic we talked about. Averaging earlier as noise reduction. Sums and averages, they're equivalent. It's just a constant multiplier in front of the average gives you the sum and vice versa. Quartile functions, so there's lots of these things. Now, one important thing is that oftentimes you're going to have to deal with matrices, okay? In linear models, you're going to see pretty soon, we're gonna do a linear model from scratch, computing the estimates of the effect sizes. But matrix multiplication is different from numerical and vector multiplication. That's why, just remember for now that if you have two matrices and you want to multiply them, you use star, but it needs to be bound on the sides by a percent sign. This means multiply them as matrices. If you skip the percent sign, it will still multiply these component-wise, which is not equivalent to matrix multiplication. Just keep this in the back of your mind. You will get different results, and most likely incorrect results, but R is not going to complain. It says, well, you want to multiply this component-wise, I'll multiply it for you. So, anyways, when you solve it, the solve method is a very efficient representation of matrix inversion, finding the inverses of the matrices, or solving linear equations like this, where this is the coefficient matrix, that's the right-hand side. The question is, what's the solution? Well, run this matrix against the right-hand side, gives you the solution. And there's all kinds of things, row sums, column sums. Okay, here is an NA, okay? R allows you to specify what is the coding for missing values. It could be, for example, a period, dot. It could be NA. It could be a string -999. It could be anything that the machine generates or something. And you see, this is how we would compute the mean. So this is very interesting, okay? Apply the function mean to this data frame, column by column, okay? And go ahead and remove the missing values. NA.RM stands for not available, remove them equals to true, indicates remove these because you can't compute the mean of something that has a missing value. You can say skip over the missing value or impute the missing value, but you can't compute an average of something that has character strings in it. All right, so again, the column B here had a missing value, but you essentially skip it to compute that its mean is 4.75. Let's skip over some of these things. Strings, we can deal with strings. Okay, let me see. All right, there are some examples of simple plotting. We're going to come back to this. Does anybody know the notion of quantile probability plots? So, suppose you have two samples. Sample 1 comes from one hospital and sample 2 comes from another hospital. You want to know are the distributions of these two samples, if not identical, similar? So in other words, was there a site-specific effect in my measurement? Think about MR scanners. You all deal with, you know, some kind of a digital brain images. People generate phantoms. They literally look like this, except that they're a little bit more mushier and they have a little bit of structure in it. They can put a celery stick in it, they embed it in paraffin. They're literal models, and these travel from one location to the next, and they get scanned so that the scanners get properly aligned to generate similar values. But this is not necessarily guaranteed, and the QQ normal plot allows you to collect a sample from the same population or the same cohort and essentially generate the quantile functions, and the quantile function gives you the first percentile. What's the value of the first percentile? So the value of my measurement, think about some kind of a cognitive score, that gives me the smallest 1% of the data is below, and the 99% of the data are above it. Then the second percentile, 2% to the left, 98 to the right. Third percentile, etc. So that's the quantile function. Imagine doing that quantile function for the two locations, or for the two sets of subjects or something. And then you plot quantile of the first case versus quantile of the second case, and if you get something that looks like this, linear and bisecting the entire space, this means that you have the two distributions are very similar, and you have a good alignment in your scanners. They're calibrated. You know, things are nice when you have linear associations of the quantiles. These are not the values of your function. These are the quantiles, okay? And you see, when you get something like this, it basically says, yeah, except at the tails, these processes are equally distributed. So they're equivalent in distribution, not in values, right? Is everybody kind of with me? So this is an important thing, and the function is very simple. It's just, you know, in this case, we are actually, so X is a normal distribution, 1,000 observations. Y is a non-normal Cauchy distribution. And then you plot the QQ normal plot of X. It basically says, yes, X is normal because it's linear. But look at the QQ normal plot of Y, which was the Cauchy distribution. Nothing to do with a line bisecting. This is called an S shape, which simply means that the Y variable is very, very non-parametric. It has nothing to do with a Gaussian distribution. Very distinct. So you can't use linear models. If these were your residuals, you've got a problem. Too much signal is left in the residuals. Okay? So these are diagnostic plots, essentially. And again, the QQ plot, X versus Y, kind of reports that. Here's another version that kind of shows, you know, very, very non-equivalent things. Low-level plotting commands. Outline does oblique line, just like the line that we saw earlier. Oblique line is a line that's slanted. It's not horizontal or vertical. Yeah? For which one? Up? Okay.
It means that if we have 2 points of data, so if the distribution are the same, we should get a linear.
Yes.
Okay. So if we have one data set and we have some augmentation there, like shifting, rotation, or something like that, so almost similar distribution. We are getting the linear.
Did everybody hear? Okay, so that's a good point. Let's do an experiment right now. The question was, what if one of my axes represents the quantiles for the real data, and the other axis represents the quantiles of a linearly transformed version of the data, right? Is everybody with me? So what does everybody think is going to happen? We're going to do this experiment right now. But do you think it's going to be like this, or is it going to be more like S-shaped like that? So the question is, linear transformations are most of the time preserving of the distribution, you guys. If you take a normal variable and you linearly transform it, it remains normal. So this kind of tells you a little bit that we're not going to see that. We're going to see more of the same. In fact, let's just go ahead and do this real quick. So I'm going to go back to the RStudio, and let's go ahead and grab the settings over here. So I'm going to do several examples for you. The first one, let's call X1 the first series. Oops. Oh gosh. Escape if you want to kill a line. Hold on. Okay. Oh, escape doesn't work here. Oh my gosh. So on a Mac, how do you... Okay, I'm not sure. I think I pressed function escape on a Mac to cancel the line. So what I want to do now is I want to have, suppose x1 is this variable that has, let's just plug in it R normal, and then let's say 1,000 observations. Let's specify the mean to be, let's say 100, and standard deviation of 10. Okay, so let me just do a histogram of this, just to show you what this looks like. Hist of x1, you know, just like you expected. Centered at around 100, the spread is about 10, so you see 65% of the data is between 90 and 110, right? Okay, and then I have, if you aggregate, if you stack all of these things together, they're going to go up to 1,000, right? Because I took 1,000 random observations. So the first question that he asked is, what happens if I linearly transform this variable? So let's go ahead and say y1. Y1 is going to be, let's say, how you want to transform? Let's say minus 13x plus 17. Look, remember x is a vector, you guys, so I'm doing vector arithmetic here. I'm multiplying every element of the vector x by minus 13, and I'm subtracting 17 of the result, right? So let's go ahead and x1, of course. See, it tells me I haven't defined x, I have x1. So I got to up key to get the previous command, and then say x1. Okay, now let's go ahead and do a QQ plot of x1 versus y1. And just like we expected, this is, you know, this is mostly linear, as you can see. It's not S-shaped. The other thing that I can do is I can do a histogram of y1, just to show you what that looks like. And just like we expected, the histogram shape is not changed, it's the same distribution. Remember, the 17 simply took the distribution and moved it 17 units to the right. The minus 13 took the distribution and stretched it a little bit. It scaled it up. Okay? So, but this doesn't change the distribution. It changes the parameters of the distribution, right? Because they're both normal, except that this one has a huge, in fact, let's just do a summary of y1. Or, I don't know, SD computes the standard deviation. Remember, the standard deviation of the original process, x1, was 10. Oh, and by the way, R is a case-sensitive language. If I do x1 lowercase, it's going to say that I don't know what x1 is. It needs to be capital X1 the way it was defined. So remember, we started with 10, And now look at this. We randomly sampled from this normal distribution, and we requested the standard deviation to be 10. It ended up being slightly higher than 10. Why? Because it's random observations. You randomly sample. So there is no way to guarantee that the sample of 1,000 has exactly standard deviation of 10. There is floating point arithmetic here. Anyways, the second the distribution of the linearly transformed data, however, is huge, 130, right? And it's way shifted off because of the negative multiplier. But if I now take a log, if I take a log of x1 and I call this y2, y2 is log of x1. Now, that's a nonlinear transformation. This is a linear transformation which does not alter the distribution. Taking a log of a variable is everybody knows the log function, right? You guys, very slowly increasing function. In fact, one of the slowest increasing functions with x is defined only for positive arguments. Now if I do the QQ normal plot of these two, it's going to be S-shaped because the distribution of y is known as log normal distribution. It's not Gaussian. It's log of a Gaussian. Make sense? So let's go ahead and do a QQ plot of x1 and y2 now. And you see the scales here. See, this is not linear. Does everybody see? Look at the scales, you guys. This is not to scale. This is quite curvilinear indeed. It's not S-shaped, but it's not linear because of the fairly compressed y-axis that we have here. Because remember, log of 100 is 2, but let me just see, x was what? This is the natural log. The base is e in this case.
I think if you change x1 to x2, I mean, the terms, after applying the transformation, I think maybe because they curve.
Oh no, we can make this.
Because the value is, when you are getting log of the small value.
No, the reason why this is compressed, you guys see, this only goes between 4.3 and 4.9. The log function is very slowly increasing, right? So if you go from 100 to 110, it's going to increase very, very little. That's why the y2 variable has such a small, tight, between 4 and 5.
Let me just...
Maybe there is a better example.
The thing is, maybe the log is taking just the value, just taking the logarithm of x1, like element ones.
Yeah.
So it's basically just shrinking down the value, but it doesn't really change the distribution shape, isn't it?
It changes the distribution because remember the log. See, this function, the linear function, changes every 2 observations exactly the same, but the log function doesn't because it's not linear. So it changes less as you go along, and it changes rapidly in the beginning and then less. You know what I'm talking about? This function changes the values at exactly the same rate. And I know this is not the best example. We can come up with other examples that kind of give you a more profound, or maybe, let me see, let me just see, how about if I do this? No, this doesn't change this. Yeah, so there could be a better example. I just need to think about that. To show the more non-linear behavior of the QQ normal plot. But the important thing is to find out if two distributions are the same. Now, in this case, we know that this is normal, this is log normal. They're not the same things. They're totally different. They're related, but not the same things.
X1 is coming from 0 and 1.
No, x1 is coming from it's not 0, 1. It could have been 0, 1, but I on purpose changed it to 110. So the center is at 100, give or take 10. If you do this, you guys, it assumes that x is Gaussian. If you just do this, now it's 0, 1 mean. 0 mean, 1 standard deviation. You don't have to specify them if you're talking about the standard normal. But if you have non-standard normal, you got to specify them.